Hi, I'm Mr. B. After watching this video, you will be able to both draw and label potential energy diagrams. Potential energy diagrams graphically illustrate the changes in enthalpy that occur during a chemical reaction. Remember, chemical reactions may be either endothermic, which means the reactions absorb heat energy, or they may be exothermic, which means that the reactions release heat energy. Consider this example from a recent Regents examination showing the potential energy diagram for the reaction between methane gas and oxygen gas to produce carbon dioxide and water. This reaction releases 890.4 kilojoules of heat energy. On the graph, the y-axis represents potential energy, while the x-axis represents the reaction coordinate. A reaction coordinate simply indicates the progress of the reaction. Arrow A represents the amount of potential energy contained in the reacting molecules. Area B represents the activation energy, where the activation energy provides colliding molecules with enough energy for effective collisions to occur, where effective collisions allow reactants to be converted to products. According to this particular graph, the reaction is reversible. So arrow C represents the activation energy for the reverse reaction. Notice that the activation energy for the reverse reaction also includes arrow D, where arrow D represents delta H, and arrow E will represent the potential energy of the products. In order to calculate the value of delta H, simply subtract the potential energy of the reactants from the potential energy of the products. It may be helpful to use the following mnemonic, where delta H will equal pepper, PEP minus PER. Now a few words about effective collisions. According to the collision theory, in order for effective collisions to occur, reacting molecules must possess sufficient energy and be in the proper orientation. Consider this illustration of a reaction between chlorine gas and hydrogen gas to produce 2 moles of hydrogen chloride, releasing 92.3 kilojoules of heat energy. Initially, the colliding molecules collide ineffectively. This is due to the fact that the molecules are moving too slowly, they don't possess enough force, and they're not in the proper orientation. However, when the molecules collide effectively, an activated complex will form, where an activated complex is an intermediate species where the orientation and energy of reacting molecules are sufficient to form product. Placing the species on a potential energy diagram generates the following arrangement, where the molecules of chlorine gas and hydrogen gas represent the potential energy of the reactants. The activated complex is at the top of the graph. This implies that the activated complex contains the maximum amount of energy possible in the chemical reaction. And of course, 2 moles of hydrogen chloride will represent the potential energy of the products. In this case, the delta H will have a value of negative 92.3 kilojoules. To determine whether or not a reaction is exothermic or endothermic, simply refer to your table of heats of reaction. If a reaction has a delta H value that is negative, then the reaction is exothermic. If the reaction has a delta H value that is positive, then the reaction is endothermic. You know, uncontrolled exothermic reactions can lead to devastating consequences, as is exemplified in this video clip of an accident at a petroleum refinery. Potential energy diagrams are also used to describe reaction kinetics, specifically the effect of a catalyst on reaction rate, where a catalyst will provide an alternate pathway for the reaction to occur. This results in a lowering of the activation energy. The really cool thing about potential energy diagrams is that if you understand exothermic diagrams, you certainly can understand endothermic diagrams, because endothermic diagrams are the reverse of exothermic diagrams. This is what I mean. Consider a reaction where ethene is being formed from its elements, carbon and hydrogen gas, by absorbing 52.4 kilojoules of heat energy. The potential energy diagram for this reaction is drawn as follows, where the potential energy of the reactants are represented by arrow 1. The activation energy for the forward process is represented by arrow 2. Notice that the activation energy for an endothermic reaction also includes delta H, which is represented by arrow 3. And of course, the potential energy of the products will possess more potential energy than the reactants and is written higher on the graph as indicated by arrow 4. Not listed here is the energy of the activated complex, which once again represents the total amount of energy possible during the chemical reaction. Now to summarize, an exothermic reaction releases heat energy, an endothermic reaction absorbs heat energy. Delta H is equal to PEP minus PER. An activated complex is a transitional species between the reactants and the products. Activated complexes will possess the greatest amount of energy during the chemical reaction. A catalyst lowers the activation energy by providing an alternate pathway, thus increasing the frequency and effectiveness of collisions. This concludes my explanation of how to draw and label potential energy diagrams. Hopefully this video has been helpful. Thanks for watching.